right, let's take a look at section 3.3, and this is where it all starts getting good. This is where we start talking about the mole. I will say this, if you need to go back through, I've put some of the previous tutorials from last year on there that may help you out. But let's take a look at 3.3 and walk through a few things here. Now, first of all, this is the definition. 1 mole is the number of atoms in exactly 12 grams of pure carbon-12. They randomly chose that amount to count up the number of atoms. And when you take a look at it, this is the actual number, 6.022 times 6.02214 times 10 to the 23rd. We use 6.022 times 10 to the 23rd. We don't need to go past 4 significant figures at all. You also should be aware that they sometimes just call it Avogadro's number. And you also need to be aware that just like I say a dozen is equal to 12, I can say that 1 mole is equal to 6.022 times 10 to the 23rd of anything. It doesn't matter what you put on the end of these, it's just that number. Now, we talked last year about how huge that number is, and they say 1 million seconds represents a span of 4 million times as long as the Earth has already existed. 1 mole of marble is enough to cover the Earth to a depth of 50 miles. That's crazy. But it also should give you an idea of how small atoms are when you take a look at these, that these are 1 mole of each of these things. And these are just petri dishes. So get an idea of this. Now, you should be aware of this. Just like a dozen, you don't know the weight of a dozen until you know what you are dealing a dozen of, right? So if I say that I have 1 mole of iodine, that's going to have a different mass than if I have 1 mole of mercury or if I have 1 mole of copper, because they all have different masses per 6.022 times 10 to the 23rd atoms of them. I just think it's kind of cool. Now, it's always good to just do the critical thinking parts. I'm not going to walk through that with you because, it's you thinking through stuff. But if you know the number of particles you have of something, you can figure out the moles, because there's always 6.022 times 10 to the 23rd particles of something. Now, they show you here, oh, by the way, aluminum, if you took 6.022 times 10 to the 23rd, you get 26.98. Same with copper, but this time you get 63.55, or iron, 55.85. I don't want to spoil the surprise for you here, but all those numbers are the numbers that are underneath each element on the periodic table. So we already know that that's the number of grams per 1 mole, or 6.022 times 10 to the 23rd atoms of that thing. Now, you can do calculations if you know that 6.02 times 10 to the 23rd atoms, and there are, for every 1 atom, it weighs 12 atomic mass units. You can come up with the mass. I want you to be familiar, because they like going back and forth between formula mass units and atomic mass units and grams per mole, because typically what we learn is, oh yeah, on the periodic table it says 12.01 grams per mole, right? But the same thing can be said that there's 12.01 atomic mass units per mole, or formula mass units per mole, right? So when we're doing problems, just be aware of it, and that's why I even paused this right here. Again, right here, they're saying they want to calculate the mass of 6 americium atoms. Now, that number that's underneath there, that's the number of grams per 1 mole of atoms, but it's also the number of atomic mass units per atom of that thing. So I could also say, remember, for carbon, I could say that carbon is 12.01 atomic mass units per 1 atom. The ratio is exactly the same as saying 12.01 grams for 1 mole. And remember, 1 mole, we could also say, is 6.022 times 10 to the 23rd. So if you're getting a little bit confused by this, just understand that this right here, this is a statement that's true as well. Now, they go back through, and I'm not going to go through the example itself, but I would suggest you go through it or take a look at it on your own. So this is a problem a little bit farther down the page that looks kind of like what we've seen before. Do you see how it asks us, hey, you have 10 grams of aluminum, and they say, tell us the number of moles of atoms and the number of atoms. Now, this is really important, because if you say the number of moles, it's the number of moles of whatever particle you have. So if they say the number of moles of atoms, don't think to yourself, oh yeah, that's the number of atoms. No, number of atoms is that thing. If they said, tell us the number of moles of cookies, that would be that we're dealing with the number of the moles of cookies, not how many cookies we actually have. So this right here should seem pretty familiar, because if they give us 10 grams, and we're going to set up in our little table, they give us 10 grams, and we typically do little train tracks here, and we go, oh yeah, there's 10.0 grams of aluminum here. Then we look on the periodic table, and do you see how it's 1 mole of aluminum for every 26.98 grams of aluminum? Again, this is the molar mass, and when we cancel grams of aluminum and grams of aluminum, and we take this and divide it by this, we end up with a number of moles of aluminum. Now, we could keep on going if we wanted to, and we could just go, all right, 1 mole of aluminum. Well, we know for every 1 mole of aluminum, there are 6.022 times 10 to the 23rd. I feel like this is not atoms. I feel like writing over the top of something else is not the greatest. However, you can also do it in 2 steps, which is what they do right here. They take this number, the 0.371, and they're like, all right, because they asked you, and you could look it up here and say, this is part A, and this is part B, right? Because they're asking that, this is our answer for A, and then this is what we're going to be solving for B right here. So we take the 0.371 moles, we take 1 mole of 6.022 times 10 to the 23rd, and we end up with this. Now, I'm not going to go through every single example in here, but I want you to kind of do that on your own. But you can go through these, and then if you want to, they show you examples that you can click on down below as well. But this is just showing you how you can go from different units. Now, notice that and they'll do this on the AP exam, and instead of starting off in grams, they'll say, oh yeah, let's start you off with milligrams, and they want you to go to atoms, right? So they say a microcomputer chip has 5.68 microgram or milligrams. You could start off in your table if you're doing this by going 5.68. Is that micrograms? It's actually milligrams. Oops. Of silicon, and you could work your way across step by step. Now, we don't have a conversion between milligrams and atoms or moles, but we do know that there are 1,000 milligrams of anything in 1 gram of that thing. So we can just go like this, and our first step is to convert to grams, and then if we keep on moving, we go from grams. And again, I would say this, when you're doing this, do not break them apart. And if they're asking you to go all the way to the end and tell you how many atoms are present in the chip, don't go here and stop right here, and then stop right here, and then stop right here. Do it all in one step. It saves you some chances from making mistakes. So all you need to know then is what is the molar mass from the periodic table of this, which they actually, I don't believe they've written it right there, 28.09 grams of silicon for every 1 mole of silicon, and then the last step will be converting to atoms. All right, so that is 13.3. Let's move on to 13.4. Again, hopefully this is all kinds of review for you, but the molar mass is just the number underneath everything on the periodic table. And if you have a compound, you add those molar masses together to get the overall molar mass. Now they gave you, hey, what if we had CH4? Well, just as if you took me and then you took one of my students and you wanted to figure out what our combined mass was, wouldn't you take my mass and add it to their mass? Well, it's the same thing here. I have CH4, wouldn't I take the molar mass of carbon, which is this right here, and wouldn't I add it to the 4 molar masses of hydrogen, 4 times 1.8, and add it all up, and this would be the molar mass that I'd use for this CH4. Another way of saying that is that there's 16.04 grams of CH4 for every 1 mole of CH4. You also should be aware, just because I want you to get used to this, is that instead of using grams, you see how they could have used atomic mass units per atom if they wanted to, or formula mass units. They could use these. Now, once you have the molar mass down, this is literally the number of grams per mole, right? So we could say 16.04 grams per mole, and then in a problem, if they give us grams or moles, couldn't we move towards the other thing? In your notes a while back, I think from last year even, we showed you that you can go between grams and moles by using the molar mass or the formula mass or whatnot. And you could go between moles and particles and by using Avogadro's number, or 6.022 times 10 to the 23rd. Remember, these particles can be either atoms or molecules or cookies or whatever. Sometimes we get confused because we're like, how could you have 6.022 times 10 to the 23rd atoms be the same as 6.022 times 10 to the 23rd molecules? And again, let me remind you, a dozen is a dozen. So if I have a dozen apples or a dozen oranges, that's 12 of each of those things. If I have a dozen atoms or a dozen molecules, that's 12 of each of those things. If I have 1 mole of those things, and I could stop right there because I don't want to spend more time with that. So molar mass is pretty straightforward, and you should be able to find it from the periodic table, and this should be a review from last year. Now, if you take a look at the interactive examples right below, they're just kind of doing this again. So you might want to just look through it and see that you feel comfortable doing that, and then go to the next example. Again, they're giving you different things that you're adding up together to get the molar masses. But let's camp just briefly with molar mass and molecules. And I'm going to say this to you here. I'm not a fan necessarily of them breaking these steps down into individual steps. I like doing it all in one step unless they ask you, hey, tell me the number of moles and then tell me the number of grams or etc. Which in this particular problem, when you look at it, they say blah, 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 scent of bananas, a molecule, blah, 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 and they give you a whole bunch of stuff, and they tell you bees release about 1 microgram of this compound when they sting, blah, 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 and how many molecules and then how many atoms of carbon. So there's 2 separate things here, and they tell you that the mass of isopropyl acetate, which by the way, that's kind of cool to know, is 1.0 times 10 to the negative 6 grams. In 1 microgram. They've done that conversion for you. And why is that a big deal? Well, if you start off in your problem down below here, do you see you start off with your 1 times 10 to the negative 6 grams of this isopentyl acetate? Well, you have to go to your periodic table, and if you notice here, however many of each atom you have, you get the molar mass and you multiply it by that number. So if you have 7 carbons, you multiply it by 12.01, right? Because it's 12.01 for every mole of carbons. Same for hydrogen, same for oxygen. And by the way, in case you're getting confused here, they decided to use, and we use this all the time, molar mass, which is the number of grams per mole, right? They could have given us a problem that would have been probably smacked us around a bit, and instead of giving us the number of moles, they could have given us the number of atoms, and then they could have given us a conversion between, and we would have used atomic mass units per atom as opposed to this. And if you don't understand what I'm saying with that, don't get too hung up on it. But what I am telling you is this right here, if I were doing this problem, I would do this. I would not stop and get the math right here and go to the next step. I would go, hey, I'm already at moles. See where I'm at moles right here? So there's moles up here. So then I go, oh yeah, for every 1 mole of C7H12O2, sorry, the pen is acting up a little bit here. Blame the pen, right? There are 6.022 times 10 to the 23rd molecules. Now they talk about units, but the units we're using here are molecules. So we right now, since they asked us how many molecules there were up here, we could get an answer, and essentially that would be answering A right here. But then they ask us how many atoms of carbon there are, and this is kind of a big deal. So as long as you have a conversion, it doesn't really matter where you're starting. So if I have 5 times 10 to the 15th molecules of C7H14O2, I know that if I take a look at my molecule here, the C7H14O2, don't I know that there are 7 carbon atoms for every 1 of these C7H14O2s? And my handwriting is not going to help you. We could also have said there's 14 hydrogens for this, and we could also have said there's 2 oxygens. They happened to ask us in the problem, they wanted to know how many carbons there were, right? So see right here, they use the conversion between 1 molecule of this and 7 carbon atoms. Now they got a little lazy here, and see how they've not put on the end of this the C7H12 or H14O2, although that didn't help you. They should have that on there because that'll make it a little bit easier to realize, oh yeah, for every 1 of these, I have 7 carbon atoms. So that has been the end of this. This has, again, hopefully been reviewed for you. Hopefully this helps. Take care.